An earlier video described air-to-air tracking using an approach enabled for the first time by digitization that was introduced in the 1970s. Widely misunderstood and thus considered suspect by program managers responsible for radar development in those days, it has stood the test of time, having been incorporated in all modern radars being built by a major supplier today. That first video included results obtained with GPS as well as radar data, but this one is focused on the 1970s innovation for radar only, specifically antenna influence on accuracy of cross-range dynamics. Concentration here is aimed at airborne operation, but with different parameters and conditions, these vital principles could be used across a broad class of applications. The radar provided updates for target state a couple of dozen times per second. The main performance limitations here are from cross-range directions, that is, in a plane perpendicular to the line of sight, LOS. They are influenced by many contributing factors, but to avoid distraction, descriptions here will concentrate on two issues of primary importance: degradation in LOS measurements and inexact antenna steering. To see why those are dominant, first look at the diagram showing a point target in a plane or view like the one just mentioned. In that view, the antenna to target sight line shows up as a discrete dot. With fairly accurate knowledge of radar range, R, we can set the apparent distances along directions JB and KB proportional to products of R multiplied by those small angles. We don't need trig because in order to track using a narrow beam antenna, those projections must remain always within that narrow cone. So as long as we know the direction of those crosshairs JB and KB, we are able to calculate the instantaneous interceptor to target vector in 3 dimensions. Immediately, the calculation is degraded by anything disturbing the placement of that discrete dot. In the earlier video, I mentioned amplitude scintillation. Radar echo strength can change by well over 10 dB in just a few milliseconds. Without monopulse, antenna squinting occurs sequentially, left and then right for azimuth, up and then down for elevation. Sudden changes in signal strength make the angle measurements extremely erratic. From experience, I know that track continuity isn't a problem, and there's a simple reason why. By characterizing target dynamics over a few seconds, with that previously mentioned couple dozen hertz update rate, the tracking algorithm is effectively averaging a big collection of those zigzag indications. Position error is thereby reduced by an order of magnitude. So the antenna can keep putting the target inside the beam. Also, because a long-range measurement accuracy is adequate, Doppler as well as range gate placement is dependable. Cross-range derivatives are a different story, though. Since noise has greater effect on rates, cross-range velocity estimates are more turbulent, and acceleration components suffer still more. Now for the second of those disturbing factors. Not only is the dot jerked away from the crosshairs, but the crosshairs themselves aren't positioned exactly as intended. Before covering that in detail, I'll show a way to compensate for it. For those with a copy of my 2007 book, the accompanying sketch matches figure 9.2 of that. In any case, though, it's easy to understand. First, let's take into account how stabilizing a radar beam implies a consistent direction spatially. If, for example, the aircraft pitches up, then, relative to the airframe, the antenna has to be steered down. More general rotations will cause the crosshairs to have some skewed direction relative to horizontal and vertical directions, and relative to airframe axes as well. The departures PA in azimuth and PE in elevation shown in the sketch are not the same as beam steering controller errors, but they can be computed. Exactly how depends on the gimbaling arrangement. Note how that compensation method relaxes the need for highly responsive stabilization control, which would otherwise be imposed by using a loop within a loop configuration. The scheme just provided tolerates beam steering imperfections, provided, of course, that they are monitored. Tracking readily equates intended antenna direction, the estimated target location at measurement time. That has to be compared against the pointing servo information at that same time. Notice the implicit requirement for synchronization. While gimbals and radar algorithms may not be mechanized according to a unified time base, the synchronization task in that case is not trivial, but it is crucial when servo bandwidth is constrained. Without correct compensation, servo errors will be falsely attributed to target motion. So, you gotta counteract it. The compensation could be simulated by modeling on-ship interceptor rotations and servo transfer functions, but that level of detail is unnecessary. As long as those response errors are being counteracted, where they came from and how they behave won't matter much. To illustrate that, a scenario will now depict two flight paths: an interceptor, plane carrying a tracking radar, at 30,000 feet altitude, and a target, tracked object, not necessarily a target in a military sense. Directions for scenario geometry are expressed with respect to the interceptor's path along its fuselage reference line, FRL. Interceptor and target speeds are 400 and 300 knots respectively, both horizontal, with the target velocity 25 degrees off from the reference interceptor FRL axis. Ground tracks of the two paths would eventually cross in azimuth if the scenario continued long enough, but the target is at a higher elevation. Initially 10 nautical miles away, it is located off FRL by 60 degrees in azimuth and 20 degrees upward in elevation. The interceptor is in a coordinated right turn, starting from an initial 15-degree roll, depicted by a short black line in the front elevation view, and slowly increasing for 30 seconds after. Those conditions were chosen arbitrarily. Any situation demonstrating realistic behavior would suffice. The scenario in 3 dimensions will unfold in 4 views, beginning with the figure you see now. The top right is a conventional PPI view with the abscissa, horizontal axis, along a lateral direction and the ordinate, vertical axis, forward. Visualizing this will be easier if I say that lateral direction is east for a northbound interceptor. The front elevation view at lower right has an abscissa, again lateral, while the ordinate now symbolizes altitude. To the left of that, with ordinate and abscissa line colors changed as a reminder of different directions, is a similar view but with its abscissa line across the wings instead of horizontal. That's correct perspective for a pilot, but aside from a horizon line slant opposite to on-ship bank angle, the lower left view otherwise has no further resemblance to the primary flight display. For that plus other reasons, distorted scaling, appearance of the target, etc., the initials PFD are in quotation marks. Even the green color used here is a departure from the horizon line appearance, blue above, tan below, for a PFD. With on-ship always at origin, instantaneous scenario conditions will evolve only gradually with the scaling used for the 3 views just described. where path appearance varies by seeing it from different angles. The upper left view, however, has a focus and a scaling that maximize visibility of displacements off crosshairs. Again, as a reminder for changed orientation of azimuth and elevation reference lines, they have a different color. This time, a lighter shade of blue, and the graphic starting now will proceed from the initial frame you've been seeing to step-by-step progression of the chosen scenario. For several discrete steps, you can see the chosen scenario slowly evolve. Projection of the target gradually moves in the lower and right-hand views, while the horizon line at the lower left starts to change with the increasing interceptor roll angle. The only view changing abruptly is the one showing apparent radar cross-range projections, confused by either or both of two degradations. The dot is off the crosshairs, mainly from amplitude scintillation if the antenna isn't monopulse, and the antenna doesn't point as intended. That's symbolized by a magenta-colored dot, and the total error, with or without compensation, is represented by a red-colored dot. Each dot was generated from a random Gaussian sequence of independent values with zero mean and standard deviation at 0.3 of a degree. For this case being shown here now, antenna pointing error was compensated, so the magenta-colored dot value didn't contribute anything to the position of the red dot. Next, you'll see things changing with a series of discrete updates at short intervals. Again, the right-hand views have scaling that produce only gradual changes, and it's difficult to notice a slow growth in the lower left view's horizon line slope from increasing interceptor roll. As expected, only the upper left view shows much action. You won't have to watch as hundreds of these updates unfold because, after the pattern is clear, we fast forward to a time when the scenario is closer to completion. Here goes. Jumping to this later stage of the action, you suddenly see greater increases in the horizon line slope, plus a spreading of all red target location history indicators. In the radar view, though, I purposely made all past projections vanish and show only the instantaneous ones. After witnessing how the updates jump around, you'll see the full history of all at the end. The magenta and red dots dash up and down, left and right. Now, as I promised, you can look at where those dots were all that time. With each at 0.05 radian RMS, 3 sigma at about 0.15 looks right. A few things to realize now. The span of red points is no greater than the magenta values because, with antenna pointing error being compensated, the magenta points contribute nothing to total cross-range degradation. I'll expand on that very soon, but first I illustrate that compensation more explicitly. Suppose imperfect antenna pointing is the only reason for dot off crosshairs displacement. The next one you're about to see is with RMS degradation from scintillation or other similar sources set to 0. Here's the rerun. As you'd guess in advance, we're letting the antenna sightline go all around, but compensation ensures that the total error will stay as 0 throughout. After what you've seen before, there aren't any surprises here. Stepping through early updates and then jumping closer to the end, to stay visible among all the magenta dots, the red dot is replaced by a black square. Just what's expected, but it's worth repeating once again. The opportunity to recover from imprecise antenna steering. Just don't forget the implications about needing very accurate synchronization. One more run to make now. Restoring the scintillation error, but this time allowing the antenna pointing error to remain uncompensated. Everything seems to look similar to the first run until the full history of error is shown at the end. Two separate error sources with equal RMS values now produce a total RMS amplified by the square root of 2, and that's evident from this view. Now for some ramifications. Two independent 0.3 degree error sources give RMS angle error slightly over 7.4 milliradian. For both azimuth and elevation, that introduces another factor of 1.414, bringing the angle error above 10 milliradians. Because that causes tracking error, adding that effect would increase the results still further. But as noted before, summing in any tracking algorithm dampens that contribution, and adding unequal variances always suppresses the impact of smaller inputs. Consequently, this example will continue with just 10 milliradians. For derivatives, however, rapid noise variations cannot be as readily dismissed. Velocity estimates benefit from averaging but less than position, and acceleration still less benefit than velocity. Achievable performance is limited because errors in cross-range target velocity and acceleration are proportional to distance. At 10 nautical mile range, 10 milliradian angle measurement error corresponds to 0.01 times 10 times 6,080 over 600 feet raw measurement cross-range target distance error. With responsiveness typically required to track fast and highly maneuverable targets, velocity averaging effects are not dramatic. Error at hundreds of feet per second are realistic. A 400 foot per second error in one direction as likely as the opposite covers a possible 800 foot per second span. That easily grows beyond 1,000 since the 10 milliradian came from a 1 sigma value. Although continuous tracking is achieved then, accuracy depends heavily on quality of angle measurements, which thus far have been represented as somewhat speculative. It is now revealed that far from hypothetical, an even worse level of defects actually appeared in a 1970s development, and the truth emerged only after years had passed. For those interested, a link is shown here and a future blog on my website, jameslfarrell.com. We'll cover that topic separately in order to maintain the intended focus of material presented here. That purpose is technical emphasis on crucial stabilization requirements from a sensor being carried with high dynamics. Further extension to current applications, such as automotive millimeter wave radar, presents very different design features, conditions, and parameters, but the need for precise stabilization as well as accurate measurements will remain.